So this example is going to demonstrate the STL equal and mismatch algorithms, as well as the STL distance algorithm on various types of sequential containers, as well as also on a built-in C-style array. So as you can see here, we define ourselves vector v1, which has 5 elements, and then we copy vector v1 into dec d2 from the beginning and end of the vector using its iterator range. And now we're going to go ahead and call a little helper method I wrote called find mismatches, and that'll go ahead and compare. And you'll see in this case, it'll come back matching because, of course, D2 is a copy of V1, so that all works fine. And then what we're going to do is we're going to take a different type of container, which in this case is going to be an array, and we're going to compare the array with the vector, and it's going to come back and tell us where the mismatches occurs. And in this particular case, you can see that there are 2 different types of containers, and there really will be mismatches because, of course, they don't have the same values. So let's go ahead and run this thing so you can see what the output is, and then we'll come and take a look and see what the results are. So the first call to find mismatches will come back and say the ranges were equal, because they were, even though they were 2 different types of containers. And then the second call to find mismatches are going to come back and tell us where the first and second mismatches occur. So you can see how we're going to find some mismatches here. 10 will be okay, but 20 and 40 will not be okay, and 30 and 60 will not be okay. They won't match. So that'll tell us specifically where those mismatches occurred. So let's go take a look at find mismatches. So you can see find mismatches takes 2 template parameters, input iterator 1 and input iterator 2. And the reason for that, as you just saw, is we can actually pass in different types of containers. We can pass in vectors and decs, we can pass in vectors and built-in arrays, and the find mismatches method doesn't care. So what we do here is we go ahead and first check to see that the size of the ranges are equal. So there's a method called distance, and the distance method is going to return the distance between the 2 values. So in this particular case, it would come back and say it was 5. So they're the same. Both elements, both D1 and D2 both have 5 elements. So distance will return 5. So 5 equals 5. And then we call the equal algorithm. And the equal algorithm, as we're about to see, is going to go ahead and go through the ranges, and it should find what we're looking for. So let's say equal. So you can see here that this will go ahead and do some comparisons to see whether things are the same. And basically what it's going to do, it can be optimized to use very low-level mechanisms like byte comparison operations, as long as it knows how big things are. So notice how equal takes first and last for the first range, but only first for the second range. And that's what I was talking about earlier when I said you have to be careful with a lot of these non-mutating algorithms, that you pass in pairs of ranges that have the same size, or at least have the second range be as big, if not bigger, than the first range. If it's bigger, it's fine. If it's less than, then chaos and insanity are going to break out. So as you can see, when we call this for V1 and D2, they will come back and say, yep, no problem, ranges are equal. For V1 and A, however, they are not equal. And so in this case, we're just showing a few things. And I could have made a loop here if I wanted to. I'm just showing this to illustrate the point. But what we do is we call mismatch if they're not equal, but they have the same size. Then we go ahead and call mismatch. And what happens in that case is it's going to return a results operation. And let's go ahead and see what that results operation looks like. You can see that results is actually defined as a pair. So if everything works fine, then we're done. But if we end up not having them equal, we're going to call mismatch, and it's going to return to us a pair. And as you might expect, the pair is going to tell you where the first mismatch occurs in the first range, and the corresponding mismatch occurs in the second range. So that's what comes back as an auto here. And so you can see that we print out first mismatching elements are in the first element here, and then the second element. And those are going to be different iterators to the different ranges. So once we've done that, just for kicks, we then go ahead and we increment first and second to jump ahead by 1. And then we go ahead and call mismatch again. And this time we're going to go ahead and actually pass in an anonymous generic lambda function, which will check to see if the values are equal. And again, whenever it doesn't get a match, that will fail, and then mismatch will return where the mismatch occurred. So then it'll go ahead and tell us where the second mismatching elements occurred in that particular range. And I probably should have written this in a loop so that I could have looped through and shown where all the mismatches occurred, but I just did it for 2. Obviously, if it had run further, we would have found that there were also mismatches other places as well. And it might be fun, just make this a 50 for kicks, and then there'd be mismatches some places, but not everywhere. Okay, so that's an illustration of mismatch. Mismatch is a bit like diff, if you're familiar with the diff utility in Unix and other POSIX-based platforms, where it compares 2 things and finds places where they don't match. Obviously not as powerful as diff, but kind of the same idea.